This is Unit 2, Topic I, on implicit derivatives. And we're going to be taking derivatives of what are called implicit functions. So first of all, let's talk about what we mean by an implicit function. When you have a function that's already solved for the dependent variable, like in this case we're solved for y, we say that this function is in explicit form. If I just rewrite the function, notice this is the exact same equation, just rearranged, right? When it's not solved for y, or the dependent variable, we now say that it's in implicit form. Our goal today is to be able to take derivatives of functions when they're in this form, this implicit form. So given an implicit function, there are essentially three possibilities. One possibility is it may be possible to solve for y and go ahead and write an explicit function. For example, right here, it wouldn't be difficult to solve for y algebraically, right? We'd have x squared y equals 1 minus 4x, and so y would be 1 minus 4x over x squared. Solving for y pretty straightforward. Sometimes you can solve for y, but it's not quite as convenient because you end up, because of the square root issue, getting two explicit functions. So in example 2 here, 4y squared minus x squared equals 4. If I were trying to solve for y, I would have 4y squared equals 4 plus x squared. So y squared is 4 plus x squared over 4. And then to get y itself, we'd have either plus or minus the square root of 4 plus x squared over 4. Meaning technically I have two different functions here, right? Y equals the positive square root and y equals the negative square root. Originally, in implicit form, we were kind of masking the fact that it wasn't a true function. For any input x, there are actually two outputs, y. That's a little bit less handy to work with in calculus because of that plus or minus, so we tend to try and avoid that situation. We tend to try and work with equations in this form, if we can. The third possibility is it's not even possible to solve for y, not even in an inconvenient way. And here's an example of that. X cubed plus y cubed minus 6xy equals 0. Excuse me. Because you've got both the y cubed and the y to the first, it's not going to be possible to get y by itself with just x's on the other side. You're always going to have one of those y's. So I can't solve for y in terms of just x. No matter what I do, I'm always going to have a y on the other side when I try to do that. All right, so given that sometimes we can't solve for y, sometimes it's inconvenient to solve for y, the question we would like to address is, in that case, how do we differentiate when we've got this type of form, an implicit form, that we can't or don't want to solve for y? In order to do that, we're actually going to make use of our chain rule. And just want to remind you real quick kind of what that chain rule looks like by looking at a derivative, first of all, of just a simple one, x to the 5th power. Of course, you all know how to do that. Just a simple power rule, 5x to the 4th. Now remember that when we used the chain rule, to differentiate something like 2x plus 3 to the 5th power, we essentially use that same form, right? We use that same power rule to deal with the outer function. So we got 5 times 2x plus 3 to the 4th. But then our chain rule said, multiply that by the derivative of the inner function. And I'm going to be very, very explicit this time. I have to multiply by the derivative of 2x plus 3. That's my chain rule. So I ended up with 5 times 2x plus 3 to the 4th times 2, or 10 times 2x plus 3 to the 4th. All right, let's now think about what happens when I want to take the derivative of y to the 5th power with respect to x. Notice the reason that this one was so simple was the variable in the function and the variable that we're differentiating with respect to are the same. Here they're not. So here I'm more like a situation like this. I'm going to think of it as a chain rule. I'm going to start by using my power rule, 5 times y to the 4th. But since the derivative was with respect to x, I have to think, well, y is actually some function of x. And so I'd have to use my chain rule and multiply by the derivative of that y. Now in this case, we don't know what the y is. So unlike above where I could actually do that derivative, the best I can do here is just leave that as a dy dx. And so my final answer here is going to be 5y to the 4th times dy dx. Implicit derivatives typically contain the dy dx term. So, to find the derivative of a function that's been written in implicit form, what we'll do is differentiate both sides of the equation with respect to x or whatever independent variable we're using. And once we've done all the derivatives, we know we're going to have these dy dx's in our equation. I'm then going to try and solve for the dy dx, get it by itself, so that I've got an expression for the derivative. In example 1, let's see how this works. The derivative of 3x squared with respect to x, oops, I already said it, didn't I? The derivative of x cubed with respect to x is just 3x squared. But the derivative of y cubed with respect to x would be 3y squared times that chain rule part, the dy dx, equals the derivative of 8, which is 0. So I've literally just taken this whole equation and I've taken the derivative with respect to x of everything, both sides. Again, notice this goes back to that algebraic principle of you can do whatever you want to an equation, pretty much, as long as you do the same thing on both sides, right? In this case, I took the derivative with respect to x on both sides. All right, I would now like to solve for the dy dx, and in this case, that's not going to be hard. 3y squared dy dx equals negative 3x squared. And so dy dx is minus x squared over y squared. And there's the derivative. Now I want to point out one other thing about these implicit derivatives. You're used to seeing derivatives of explicit functions, like x to the 5th. And when you take the derivative of an explicit function, there are only x's. It's the only variable in the derivative itself. Notice that when you take the derivative of an implicit function, your derivative will often contain both variables, x's and y's. There's usually nothing we can do about that for the same reason that it was implicit in the first place. Not a big deal. It just means that if you ever have to substitute in and get a value, like if you were thinking of this as a rate of change or the slope of a tangent line or something, you would have to have values for both x and y to sub in. All right. Let's take a look at a few more examples of implicit derivatives. Here I've got my x squared y plus y squared x equals 3. And the first thing that I'd like you to notice is that these are really products, right? This is x squared multiplied by y, and this is y squared multiplied by x. They're easy to miss because they're so small, but they really are products and they require a product rule. So for this first one, I'm going to have f is x squared and g is y. So f prime would be 2x. And g prime, the derivative of y with respect to x, the best I can do is just write it as dy dx. So fg prime plus gf prime for my product rule is going to give me x squared times dy dx plus gf prime 2xy. Plus my second product rule. F is going to be y squared, and g is going to be x. And so f prime will be 2y times dy dx. There's that chain rule again. And oops, let's let those be lowercase. Little g prime is just going to be 1. And I'm going to want fg prime plus gf prime for my product rule. So fg prime, y squared times 1 is just y squared, plus gf prime, 2xy. Equals, the derivative of 3 is 0. So there we go again. We've just gone ahead and found the derivative all the way through. Whoops, you know what? I just left off a dy dx. Sorry about that. Right here. Gf prime should have been 2xy dy dx. Let's fix that. dy dx. There we go. And that's still, of course, equal to 0 for the derivative of the 3. All right. I now have all of my differentiating done. What I need to do next is solve for the dy dx. And in order to do that, I'm going to keep the two terms that have a dy dx in them on the left-hand side. And then I'm going to take the two terms that don't have dy dx, and I'm going to move those over to the right-hand side. If I now factor out the dy dx, I'll have x squared plus 2xy equals negative 2xy minus y squared. And then I can solve for dy dx by simply dividing by this. So dy dx is negative 2xy minus y squared divided by x squared plus 2xy. And there is the derivative that I was looking for. Again, not surprisingly, it has both x's and y's in it. That's typical for an implicit derivative. All right, let's try a couple more. In number 3, I've got e to the xy equals 1 minus x squared minus y squared. So first of all, taking the derivative on the left, the derivative of an exponential function is itself. So first I'm just going to get e to the xy. But then chain rule. I have to multiply by the derivative of xy. I know it's really annoying, but there's a product rule again, right? X times y. So in this case, f would just be x, and g is just y. F prime is 1, and g prime is dy dx. So for the chain rule, I'm going to have a product rule here. X dy dx plus 1 times y. And there's the derivative on the left. The derivative on the right, I would get 0 here, a negative 2x, and then a negative 2y, but times dy dx for the chain rule. All right. Once again, my goal is to solve for dy dx, but before I can get the dy dx's by themselves, I'm going to have to go ahead and distribute this e to the xy so I can get rid of those parentheses. So x e to the xy dy dx plus y e to the xy equals negative 2x minus 2y dy dx. Gathering my dy dx terms on the left and everything else I'm going to move to the right, I would have x e to the xy dy dx, and I'll bring this over, so plus 2y dy dx. And on the right, I've got that negative 2x, and I'm going to move this term over, so minus y e to the xy. I will factor dy dx out of the left-hand side. Leaves me x e to the xy plus 2y equals that right-hand side. And then solving for dy dx, we have the negative 2x minus y e to the xy divided by x e to the xy plus 2y. Typical implicit derivative, again, it has both x's and y's in it. And it's a little bit messy. These are often not super simple, but they are what they are, right? All right, let's do one more example. And then I think, yeah, after that we'll use a new video for the applications. So in example 4, I'm seeing a product rule right away over here on the left. Sine x times tangent x. Or, excuse me, sine x times tangent y. So we'll set that up right away. F is sine x. G is tangent y. In case you haven't already guessed, you're going to use a lot of product rules in this section. F prime then would be cosine x. And G prime would be secant squared y, and then the chain rule times dy dx. By the way, if you're starting to wonder, why do I do the chain rule here and not there? Remember, it's because of the variable that we're differentiating with respect to. Technically speaking, even here, I've done a chain rule. I just don't usually write it. The derivative of sine x is cosine x, and then the derivative of the inner function, x, would just be 1. So technically speaking, there's a times 1 here. We just don't bother to write it. Right? When the variable's y, then the derivative is dy dx, and we have to write it. All right, product rule. Fg prime, sine x, secant squared y, dy dx. Plus gf prime, cosine x tangent y, equals, on the right-hand side, I've got 1 plus the derivative of y, dy dx. All right, let's get all the dy dx terms on one side. So these two over on the left, and then I'll have the non-dy dx terms on the right. So, factor out a dy dx. And solve for dy dx. 1 minus cosine x tangent y divided by sine x secant squared y minus 1. All right, so there are the skills areas of finding implicit derivatives. We will pause there, and in the next video we'll take a look at some applications that involve using implicit derivatives.